Yeah, today we will be discussing about the forging die design consideration. In forging, what is very important is the die design, and die design is a very complicated job in forging, especially impression die forging, or you call it as closed die forging, but basically it should be told as impression die forging. One is designing of the die, second is manufacturing of the die. These two are important, and your approach is entirely different. If you are using a hammer forging, then you have a particular type of design. If you are using a press where the deformation is at a slow rate, then your die design is different. You have to choose the materials, die material also accordingly. So, and like you make a small mistake somewhere, the metal has to flow into all the intricate shapes, and suppose it is at a higher temperature, it gets heated up, and then okay, the die gets softened, and if you are not doing it in a proper way, the die metal flow will take place, and it may result in die wear, and without much time, maybe after doing some 500 or maybe 300, 500 pieces, you may find that the die wear has taken place and it was like it cannot be acceptable. Then it becomes very complicated. Or if it is in the case of hammer forging, then what happened after a few cycles, it may break. So, for a hammer forging, you want the die material which should be very tough. Otherwise, due to the impact, it may break. But whereas for press, the metal will be flowing slowly, but it may result in, because the material will get work hardened and it may wear the material. So, what is required in the case of a die in a press forging, when we are using a press where the movement is very slow, ram displacement is very slow, is that you should have a very high wear resistant surface. Okay. Their toughness may not be that much of importance, because impact is not coming. So, it is only toughness which you wanted, high hard wear resistant surface. So, that the die surface should be hard inside that. And the thing is that most forgings require a series of forming stages, and this is called as the preforms, preforming operations, because you are not going to get, because your billets are normally in a cylindrical piece or a rectangular piece depending upon that, and then you are cutting from that and keeping in the furnace, and then okay, you are just keeping it in the die and pressing it. Okay. It is not like that most of the case, because the shape, simple shapes like sphere and cylinder, that is okay. But when you are going for components like a connecting rod, a crankshaft, a spanner, or a crane's hook, then the shapes are different. So, you cannot get that in one operation. You may have to have different preforming operations. These are called a preforming operation. And the number of preforms required depends upon several factors, including what is the overall shape. See, it is not only the shape. See, there may be the components have different sizes at different places. So, that means that result in the complexity of the shape, which we have discussed in our previous class, classification based on complexity. And third, the material itself. If the material is work hardening to a great extent, then you have a lot of problem. So, forging complexity is increased by several features, and this includes the presence of thin sections in the part. When it is thin section is there on a part, then you have a lot of problem, because it may not flow into that full length. That is one. Second thing is that this results in work hardening very high, because large amount of deformation is required in that case. Third, while ejecting, there is every chance that it may break also. So, all these problems are encountered. So, you will find that the complexity increases if there is a presence of thin sections. If there is a presence of complicated shape also, there is going to be a problem. Okay. And in cross sectional area, if there is a large variation in the cross sectional area, you are going to have problem. The part shapes that require die parting, like here, say suppose now you want that part to have a different parting line, like in this case it becomes very complicated, whereas here it is very simple. So, your parting line between the two dies, so that is crank the parting line when it comes, then you will find that there is a lot of the complexity increases. And when you come to the role of flash in forging, I have already discussed earlier, the flash is generated due to the closed die form. So, this flash which is generated, it is basically an unwanted material, because some photographs I have shown earlier. So, it is an unwanted material which after the forging operation you have to remove it. See, and in most of the cases this flash material will have a considerable volume. So, you may have that the volume of the flash may go up to more than 50%, 50% of the volume of the component. In that case, you are going to end up with a large wastage of material also. So, these type things are. And the flash which is formed, the more complex the component is, the flash will be larger. So, that is another important thing. So, for a simple component which are very, there is not much of a complexity in the geometry, then the flash amount of flash may be less. But for a large component where the complexity is very large, then the flash which is required also will be very large. The control of flash formation is very important, because you need the flash due to as I have mentioned in the last class itself, the flash is required because we cannot cut the raw material exactly as what you require. Now, when you are going to heat it, there will be some scale losses and other things. So, that also has to be taken. So, you may have to have some extra material. Next one is this act as a cushioning effect. So, it will take much of the impact when the forging is taking place. So, because the two die surfaces will not come in direct contact with that. So, that way it is safe for the die. Third, if flash is not there, the entire die filling may not be complete. So, sometimes underfilling may be taking place. Sometimes there are overfilling. If it is there, you have to remove the material, excess material, for that also comes out as the form of a flash only. So, flash is a necessary, but the flash volume should not be very large. You have to have minimum amount of flash. So, as the material begins, so this is the case how the flash is forming. This is one die, this is another die, this is the bottom die, this is the top die, and this is your workpiece material which you are having. And when the top die is, which is a movable die, is coming down, you see that it, due to the barreling effect, this barreling effect comes, it just moves sideways. Okay, lateral flow takes place, but between this is the die cavity which is coming. So, when it gets here, it gets slowly as the die advances, the thickness will get reduced. Okay. So, a narrow flash is formed around the component. This is only a sectional view. If it was a cylindrical piece, you will find that around the piece it is there, the entire piece along the parting line it is coming. So, and the material flows sideways, resulting in a flattened shape, because it has to flow between these two area of the cavity. So, it will be a flattened side, but when the die still further closes, this will get reduced more, and in the meantime what will happen, you see that here material is not filled, but as it comes down it will just flow and fill up the entire cavity. This is only a section of that, and here the metal will skirt out in the form of a flash. This is how. So, if this flash was not there, the die here and here, these two die surfaces may come and meet, and then the large amount of stresses which are developed, it may result in the die failure. So, in the final stage of the die closure, you will find that the material gets extruded out through in this direction, and this will be through the complete circumference of the piece, because this is only a section which is shown. And so, this result in flash gutter and flash land. So, this is the flash land and this part is the flash gutter. So, since we have not shown it completely, so that is the thing. And now, when you look at that, you can also see how this when it is coming, how this affects the forging load. I have discussed this, but here I will still once again think. So, when the die contact the forging load, it increases with the forging stroke. So, you may find that when the dies contact the workpiece at this stage, then the force started building up. Okay? And somewhere it goes constantly, it is a homogeneous deformation which is taking place. Of course, some amount of frictional force is also coming, but if you assume it is a well lubricated piece, okay, it is like a constant thing, and from somewhere, see this flash start formation, it touches this die surfaces, and at that time you will find the load keeps on increasing. The load keeps on increasing here, because extra force is required for the deformation of the flash. So, that is why load keeps on, and as it comes down, when the height keeps on decreasing, the load will increase. In our derivation, we have found that it has a direct relationship between the thickness. So, with the thickness increasing, the load keeps on increasing like anything, and when it is when the die is completely filled, you will reach here, but you know that you can control it by your stroke adjustment. So, but towards that part, this is the complete die closing, and you have a very thin flash which is coming, but extra material which was there, it has just flown out. So, that is the thing. So, you will find that here pressure increases very much, and for the metal to squeeze between this or extrude between that, the forces will be very large. And when you look at this, you cannot avoid flash and flash gutter in an impression die forging. So, what is required is that the selection of appropriate levels for the flash land geometry is very much necessary. So, the gap and the width. So, this is a typical something downloaded from the net. So, nomenclature for the flash. Okay, this is the material which is flowing, this is the flash. So, this is the flash gutter which is shown, where the whatever extra metal is there, it can flow and fill it up, that you will make it into a very large piece. But this part up to here which is parallel, it is called as the flash land. Okay. So, near the parting line, this width part is called as a web. One should remember this. This is the fillet radius, and this is the corner radius. The external internal draft angles are required, for otherwise you may find it difficult to eject it out. And so, after all these things are there, this flash will be trimmed out from here. So, you need to have kept it into another die for this purpose. Because this flash land and this gutter is important, because if excessive flash land is there, excessive material will be there, you will be losing large amount of material in it. But if it is less, the die filling, complete die filling may not take place. So, but you need to have an idea about what are the geometry of that is very crucial. So, the gutter must be large enough to accommodate the flash formed. See, because this gutter region, the volume of the gutter has to be very large. Otherwise, if you are by any chance, if your more material is there, then you will have problem. The component may go out of size. Okay, oversized it may come, and then the resulting that it will get rejected. But if it is less, then another problem will come. So, gutter there is no question, but flash you have to be careful with it. So, if the geometry is not correct, die may not fill completely, or the forging load may become excessive. If the projected area of the flash in the flash land is usually included in the total projected area of the part for estimation of the forging load. That is very important, because we found that when the thickness of the sample is reduced, the forging load will be very high. So, here when you are doing the load necessary for the forging operation, you have to consider the total projected area is not only of the component, but also it should include the flash area also. At least flash land area is very important. So, so that means according to that only your load will be very high. Okay. So, you have to slightly reduce it, otherwise your machine may not be able to deform it completely. Okay. So, determining the selection of, and this also depends upon the selection of the process. You may find that a large number of numerical, number of empirical relationships are available for this flash design. So, some of these are this, which has been obtained from the literature, selected empirical formulas, we can get it. These are the authors which are there, and This first two relationship, that is these two relationships, it take no account of the forging complexity. It is just for a simple diametrical or cylindrical piece where it is not for complex geometry. For simple geometrical things it is taken. So, it has not considered the complexity of the the forging complexity of the component. It has not taken place. So, this is the flash thickness and this is the flash land ratio, flash land by your the width of the flash land by the flash thickness. So, that is this ratio. In this case it is not there, but here it is 63 d to the power 0.5, where d includes the projected area, which includes the flash land region. The third formula is by considering limited number of axisymmetric forgings. So, this is basically for axisymmetric forgings, where you find that flash thickness T is equal to 0.017 d plus 1 by d plus 5 to the power 0.5, okay. And the ratio is like this flash width to flash thickness ratio, you are getting this relationship. Now, the fourth formula is used for the cost estimation procedure, as it is simple to evaluate it, and this takes care in terms of weight. Okay. So, because this is very simple, in terms of weight you can find out to determine the cost of this process. So, this fourth one can also be written in terms of the volume also, okay, as opposed to the weight. Okay. So, that is you can get that in this form instead of in terms of weight, because here now what has been written is this W is your weight, AP is the projected forging projected area, which includes the flash land also, W is the forging weight, D is the forging diameter, and Z is the forging complexity factor, which we have discussed last day. And so, flash thickness equation in terms of volume you can get this, and flash land ratio in terms of volume. So, this becomes very simple. Okay. The land width WF is multiplied by the length of the flash line for the finishing forging die. So, that is the perimeter and other things. Okay. So, that way it is used. Now, amount of flash, as I mentioned, it may sometimes go to very high value also. Okay. The cost of the material in forging is determined by the weight of the finished forging, and if there is a material wastage, then your cost of the forging will go very high. So, this loss of the material can be like in terms of flash as well as in terms of oxidation, if it is hot working oxidation which is taking place also. So, that way it is there, and you see that for simple alloys it is okay, but for very costly alloys this becomes a real problem, and in costly alloys forging also becomes difficult. Okay. So, you have to have the minimum of material loss, that is by from the flash produced during further, but further losses may occur due to scale formation for this material that oxidize significantly during the heat treatment, for hammer forgings due to bar ends and so on. In hammer forging you have to hold it at one place and then hit it. So, that way also you end up with the loss of materials. So, there are a lot of this only there. But in impression die forging, when you look at it, you will find that the flash weight, okay, that kg per centimeter of the peripheral length. See, if you look at it, it is this one. If the forging weight is less than 0.450, you will find the flash weight is something around 0.0047, okay, kg per centimeter, the periphery that length, and this is. So, you will find that when it is increasing, this number keeps on increasing, and above 45.455 kg, you will find that the flash weight is very high compared to the other cases. Okay. So, estimation of the flash for a particular forging is difficult and is usually based on experience with the manufacturer of forgings of a similar type. So, most of the case, like you cannot arrive at certain conclusive data and say that okay, the flash loss will be this much, and many times the experience of the designer, the forging die designer, that has an important influence on that. So, if he is very and that too based on his past experience, So, that is how we can, but this whatever this data is available in the literature, this will give you a rough idea about it. The amount of flash produced varies with the shape of the part, and there are two basic. One is by statistical data from our large number of experiments, and from experience we can get it, how much it will be. And another is the average value of the flash amount per unit length of the flash line for. So, that is what we have shown here. Okay. So, these two cases are there. Now, when you are designing for the flash, there are webs. See, when you look, you see that web is there. This is a piece which is there, maybe it may be a flywheel or something. So, web is there. So, these webs are thin sections, you know that. Webs are thin sections. So, refer the earlier figure. Webs are thin sections with large projected area. In the direction of die closure. And these webs are designed into the part for strength and maybe other reason, maybe you wanted to connect the rim with the hub. Okay. So, then that is the only way by having this web, and usually these webs are thin, very thin, and when it is thin and the outer rim is very thick, then you have a lot of problem. Okay. These webs add considerably to the load, and you will find that the major area taken by that is due to the web rather of a component. If it is a flywheel, the maximum area is taken by the web, not by your rim or by the hub. So, this, because of this, it adds considerably to the load requirement during forging operation because of this die contact area, and once it is thin and its area is very large, your forces has to be very large. So, that is there. So, if the finished part has through holes to be forged in, then these must be filled with webs at the die parting line. So, that is another problem. Many times in the web also, not to reduce the weight, people may put some holes also, then it becomes much more complicated. So, material in these webs is additional waste material and add to the material cost per part. So, you can say that the approximate thickness of the web, say web area into web thickness, no, there are certain from experience, no, this is from literature only, we can just get this information and other thing. The appropriate thickness is dependent upon the projected area of the holes to be filled. So, the web thickness we can get it like this simple relationship. These are all this from experience. Okay. TW web thickness in millimeter is equal to 3.54 into AH, where AH is the area of the holes in square centimeters. So, that is one. Now, another important thing, design consideration, is the allowance. See, your forging finishing operation will not be exactly as what you wanted, because in the forging die design you have to provide allowances for many things. One is for machining allowance. So, one is that machining allowance, and next is your draft allowance. There are internal draft as well as external draft allowance, otherwise the material will not come out of the die. Then you need that for radius allowance, then you need for fillet radius, so this is that. See, this figure which is shown by this dashed line, this is your final component. This is the drawing of your component, but when you are making the part, this is a sectional piece, you will have to provide extra. One is you have to provide this, surface has to be very good, so you need to have a machining allowance there. Okay. So, you have to put extra material so that it should be machined off. That is why it is called as machining allowance. So, or that is also called as the finish allowance. Okay. This amount is in addition to dimensional tolerances and must be sufficient to result in a clean surface. Okay. So, once you machine it out, you are going to get clean surface. So, that is one important thing which is, because many times what happens is that during deformation, when you are going to keep it in the final finishing die, see the metal may be in the heated condition, and when it comes in contact with your air, it may get oxidized also. So, that part has to be machined. So, machining allowance is required. Okay. The level of oxidation depends upon the material type and overall size of the forging. Now, next is your draft allowance. Okay. The draft, it is in terms of angle. So, it is a taper which is going to give. So, if you are putting it straight as per this drawing, if you are just drawing like this, then what happens is that metal will fill, you will not find problem in ejecting it out. So, you have to have a high production rate. Second thing, here it may get stuck. You may find it very difficult to remove. Sometimes it may be impossible also without damaging the die. So, these type things. So, for easy withdrawal of that, you have to provide draft allowance. So, draft allowance is basically the external draft allowance is there on the outside surface. So, that will add to that, and whereas internal draft you are giving here. So, by which the dimension of this part gets reduced, here it gets increased, but ultimately that you have to machine it off, draft allowance also. So, in general, draft allowances on the inside surfaces, the whatever is this angle here provided is always greater than that on the outside surface. That is what generally, otherwise you may face problem, because this may be very intricate shape or a complex shape and other things. So, you may face problem in removing the material from the die. So, internal draft angles are provided are always higher than that of the external draft angle. So, this is the draft allowance. If you look at this steel and aluminum alloys, in hammer die, the external draft allowance is 5 to 7 degrees centigrade, whereas not degree centigrade, degree, whereas for the internal surfaces, the allowance is higher than this. Okay, there it is 7 to 10. Similarly, in pressed dies also, internal may be 3 to 5 degree, whereas for external it is 3.5, 3 to 5, whereas for internal it is 5 to 7 degree. So, that is what you will find, that in all these cases your internal is generally higher, and say maybe like you look at niobium alloys, nickel based alloys, tolerance in all these cases are say plus or minus 1 degree and other things. So, that is also there, because those things are difficult to machine. Now, we have to look at the fillet radius. See, if you look at this, two types of radiuses are there. One is the edge radius and another is the fillet. Fillet is the internal part, there you have to provide radius, otherwise metal will not flow smoothly. Okay. So, the edges and corners in the part must have radii added to it. These radii are necessary to aid material flow and ensure good die filling. If the radii is not provided, the metal flow direction will change, and then you may find that it is not filled properly. And even if your excess material is there, and if it is going to fill properly, you may end up with certain defects at that part, because metal will come and then join as if it in a. So, due to that, you call it as lapse will take place. So, for that you need a smooth flow of the metal in the plastic stage. For that, liberal radius are required actually. And so, sharp, second thing is that if in the die also sharp corners are there, that will result in stress concentration, both for the die as well as for the workpiece material. So, in workpiece material, the design engineer will say, I want a liberal radius, but liberal radius means it will increase the material to be used. So, many times this problem will be there, and stress concentration effect will come. So, component may fail, or during forging operation your die may fail also because of the very high stress concentration which are there. So, due to this, to avoid these things and also to help in the faster forging, so your production rate can be increased, you always provide sufficient radius both for the what you call it as a corner as well as for the fillet, and normally you will see the corner radius is much lower than the fillet radius. Okay. So, in most of the case the fillet radius is higher than the corner radius. The terminology of corner and fillet it is already shown in this figure actually. So, here this is the fillet radius, this part this is the fillet radius, whereas the other is edge radius is here, the corner and other thing. So, this you have to take care of this thing. These are one of the some important things which you have to consider during the die design. Now, even this figure I have shown earlier also, because very few forgings are produced in one stage. This is the case for a this figure shows the case for forging of a connecting rod. Okay. So, the first stage you are having a billet in this form, a cylindrical billet and other things. Okay. And then you are subsequently doing many operations like this is a fullering operation, and then you may have to reduce some section for which you may do a partial rolling operation, all those things. So, sometimes splitting operation will be required, sometimes punching also may be required. In all these cases you will find the different operations are there. See, unless it is a cylindrical piece or a square piece or something very simple case, in that case it will not be a problem. Okay. But in most of these cases where it is a component to be deployed in the field for as a part of an engine or part of a machine component, then most of the case multiple preforming operation is required for impression die forging, and these are necessary. And the final operation is you call it as finisher operation. The one step before the final operation is called as the blocker die. Okay. The starting point of the forging is in a very simple shape, either a length of round or a square section bar or a billet is cut off from the bar stock, and this object of preforming is to redistribute the stock. So, the preforming operation is to redistribute the material to correspond more closely with the finished shape. And the design of this preforming dies is another thing. There is no set of standard rules and other things how to do it. So, it all comes by experience of the forging die designer. So, that is another important thing. So, but when you are designing it, you have to take care that the metal is flowing without least resistance and other things, and complete die filling is taking place. So, it is a sequence of the operation which takes place. Okay. Progress has been made in the recently, you will find lot of finite element methods are there, and CAD/CAM packages are there, where you can just design this preforming dies in a very simple way. Okay. So, those type things are there. So, that type advancement has taken place. Most of the flat or compact forgings, it starts from the billet and can be usually be produced in 2 to 4 forming stages. Okay. The first forging stage is a simple die, which may be a flat face called the scale breaking die. When you, because if it is in the hot condition, you are taking from the furnace almost all metallic materials there will be an oxidized layer. Even if it is steel, it will get rusted. And so, taking from the furnace you cannot scrap it off. So, what they do is that they just put it in a between a flat die and then just give a small impact, so that the scale will just get separated from it and fall off. Okay. So, that for that provision should be there, and most of the case the die will be, all these preforming operations most of the case will be in a single die block itself. Okay. So, the purpose of this initial is to remove the scale formation, but if it is too simple, the material can be forged in the finishing die itself. But you will find that most of the case you may have to have, because some it will not be a simple shape. Now, most of the case you may have to give a preforming operation, okay, that is which is necessary. And in the blocker, which is just the operation just before the finishing operation, is the most important thing. Okay. All other things you can do, any rough work and other thing, but here it is very important. There are some well accepted design rules for blocker cross section area. So, typical blocker section relative to finisher cross section, we can see that if the final part has thin or tall feature, then a pre-blocker may also be required, and this will have thicker sections. In this particular case, this figure, you will see that there are two fullering stages. After two fullering stages and one edger die, okay, and edging is also taking place, it results in a dumbbell shape. See, you can see that it results in a dumbbell with approximately a round cross section with an axial mass distribution similar to the finished product. So, around here it is coming. The initial mass distribution preforming stages can be done on reducer rolls. So, these things, this part and this part you can do on the using a reducer roll. Even this also you can do by a reducer roll, which uses a series of shaped rolls to elongate and draw down the bar stroke. So, from here you will find that, okay, your length is also increasing when you are doing this rolling operation, with a corresponding reduction in area in this case. Okay. After this, the cross section of the part are there to be formed to corresponding to a finished shape. This is your finished shape. So, here you may have to get this shape and other thing. You see that it is two connecting rod part in one single block, that is what they are getting. Okay. Whether a blocker die is required is usually decided based on the experience, and the blocker forging cross sections are essentially a smoothed out version of corresponding sections in the finished forging. Okay. The blocker sections are designed by modifying the corresponding finished sections. You see that this is the blocker forging cross sections and other. See, this is a simple die block which you look at it, and all the operations are carried out in a single die block. Not it is not that you will have different presses for different operation. So, maybe when one ram displacement taking place, you will remove your material from one to the other, okay, other cavity. So, this is the fullering die part which is there, and this is the edging die part here. So, here you can increase this width and other things, and this is the finishing operation. Here also edging is there, the blocker is there, then the finishing operation. So, bending, edging, blocking, finishing. These are the main four commands. Sometimes splitter also may be required in some cases. Okay. Like that many operations are carried out. So, the blocker sections, if you look at the blocker sections, the blocker and the finisher, there is not much difference. It is only a very small difference is there. So, that the blocker is designed such that in the finishing die, the minimum amount of metal flow is taking place, only what is just sufficient, because if the dimensions goes out of this one in the blocker die will not matter, but in finishing die the metal flow should be minimum. If large amount of metal flow is taking place in the finishing die, then after say, a number of forging operation, you will find that the wear is taking place, the die's internal surface gets worn off, and then the material will become out of tolerance. Okay. So, that is one within the out of the limits, and then okay, your rejection will come. So, always see to that in the finishing die the minimum amount of material flow is taking place. So, for purpose of estimating the die block size, the following cavity spacing ruling can be used. These are all thumb rules. Okay. Cavity depth dc is equal to 0.5 t, where t is the part thickness. Cavity spacing between these two die blocks, it is 3.1 into dc. Okay. And that is a die cavity. Okay. And cavity edge distance is this distance. So, you have this type of thumb rules which are there, which are generally used. If it is very large, then your die block will be very large. So, your die cost will go to exorbitantly high. But if it is very less, then the die strength also has to be considered. So, minimum distance is to be maintained. And during this gives an idea about, so it is a trial and error type thing. Nowadays, all this with the CAD/CAM packages we can do it, but the principle is like this. See, this red area, it shows your component. Suppose this shows your component. This will be your blocker die. In the blocker die, this is so that when the die closes, this metal will flow into maybe this region. Similarly, this is the blocker die region, and when your die in the finishing die is there, metal from here to flow here. That is, this A2, this region will be the sum of this metal and this metal. So, you will find that other part metal is not flowing, but only from here it is going, from here it is going. So, both extruding inside, and here it is extruding and it is being, here it is forward into this part. So, only very small amount of metal flow is taking place in that. That itself will take place as the die advances. Similarly, so that means this green value, green region is your blocker die design. And okay, of course, this you have to show it like this here also. Whereas the red one is the finishing die. In the same case also, you see that from here, what was in the blocker die, that will move here and it will reach up to here. Similarly, from here it will move here, from here it will, metal will flow into this region, from here metal will flow into this region, from here metal will flow here, here it will flow, this will flow in like that. That is how it comes. And similarly, here also when you look at it, you see that different geometry is there. This green one shows your preform or maybe your blocker die design, and the red one is your final finishing operation. So, these are some of the things when you have to look at it. Now, in one die itself, you may have sometimes, for simplicity, if it is a complicated shape, you may incorporate more than one component itself. And then by the die design, if this type of a cranked die is there, so you take care of by locking itself. So, that if this locking was not there, if it was straight like this, during pressing the metal is here. So, this die shift will take place in this way. So, to avoid that, this is where the experience comes. So, you are automatically you are going to have a die locking device also, configuration also inside this. So, the choosing the parting plane is a very important thing in this die design. First thing one has to look is how your parting line should be there for the die block. Basically, these are all for with respect to your finished for the finishing impression die and blocker die. Other cases, it will not be much of a matter, because die shift and other things should not take place. So, there are certain things which has to look into that. So, you have to very carefully make the layout of the die. Okay.